welcome everyone to this SEMNI day. Sorry for the delay again, but in any case, we are happy to host today our colleague and friend Ricardo Vinuesa. As you know, Ricardo is associate professor at KTH, Royal Institute of Technology in Stockholm, in Sweden, as well as an affiliated researcher at the AI Sustainability Center of this same institute. He's also vice director of the KTH digitalization platform, and as all of you know, well known for his work on turbulence, including computational fluid dynamics and machine learning methods, a topic about he is going to speak today. Professor Vinuesa led an influential study very recently on the impact of AI, artificial intelligence, on the 17 Sustainable Development Goals of the United Nations. And it is truly our pleasure to have him today with us. So, Ricardo, sorry for the technical problems, sorry for this delay, but apparently everything is working fine at this moment. So please, the screen is yours.
No problem at all, and thank you very much for this invitation, Elias and Irene. It's a true pleasure to present in this very nice setting. I'm going to talk about modeling and controlling turbulent flows through deep learning, and my research is funded, among others, by the European Research Council. So I'm going to start by talking a bit about machine learning and some of the success stories of this technology in many areas. For example, in computer vision, in image classification. Here we can see the ImageNet challenge, where it turns out that machine learning algorithms are much better than humans at identifying pictures and classifying them. Machine learning is very widely used in many areas, including speech recognition, economics, predictive text, etc. And maybe an interesting experience is the chess game between Garry Kasparov and the Deep Blue machine by IBM in 1997. Kasparov was the world champion at the time, and as you can see, he was not very satisfied with the outcome. He complained a lot about his results at the end. But it turns out that chess is not such a difficult game to play for a machine, because if you think of the number of moves that you can have in a particular game and the number of turns that a typical match has, one can define the complexity of a board game by taking the number of moves and raising that to the power of the number of turns. And if you look at the value of chess, which is this value over here, and you compare it, for example, with the game of Go, which is another game that has been quite popular now. It has been popularized by the machine learning work of Google and Deep Blue. And you can see that the complexity of Go is many orders of magnitude larger than that of the game of chess. So it turns out that to play this game, Go, is not enough with evaluating possible moves and finding the best one through brute force computing, which is a little bit what the Deep Blue machine was doing. You need to develop a sort of intuition and a sort of basically a certain idea of what could be the best strategy in order to be able to do this properly. So it's actually quite interesting how what they did in the Google DeepMind team, they developed what is called the Alphago algorithm. So the Alphago algorithm was based on learning from the best games of human players the most successful strategies through reinforcement learning. So this algorithm was really able to copy and mimic those best strategies, and they confronted this algorithm against Lise et al. Here in this picture that you can see, and the AlphaGo algorithm won by 4-1. So it turns out that this game, which was very challenging to play for a machine, it was expected that this would happen in many years in the future, was able to defeat the world champion quite easily. And even more impressive was the next step in the development, which happened in 2017, which is the AlphaGo 0 algorithm. And this one is not given any human input at all. This algorithm was just given the rules of the game of Go, and then the algorithm played against itself, progressively improving the performance until, as you can see here, I'm plotting the performance of the algorithm. The blue line is the Alphago 0, and the horizontal axis, you can see the hours of training. You can see that in less than 2 days, the Alphago 0 algorithm was better than any human player in this type of game. In fact, when they confronted the Alphago 0 with the Alphago, the one that had no human input at all won by 100 against 0. So this is just an example. Games are an interesting platform to test novel algorithms because they require a certain level of strategy, a certain level of intelligence, if you wish, in a very specific task, however. And what we are going to see today is the potential in more concrete applications of engineering. Perhaps if we look at the wide range of possibilities, we can actually see that machine learning is really having a very good impact in many, many areas. We can look at the 17 Sustainable Development Goals of the United Nations, and we can assess for each of the areas of these goals, what is the positive potential of machine learning. You can see all the information and all the examples in this article in Nature Communications, but essentially 79% of the targets of the United Nations can be positively affected by AI, and only 35% of those targets can experience a negative effect due to the development of this technology. Perhaps another area which I believe is quite important is that of interpretability. And that's the idea of developing models which can give us input and insight into what is the importance of each of the input parameters, and perhaps even more to have a symbolic equation that represents the effect of a deep learning model. If deep learning models are being implemented in applications that have to do with society, with sustainability, with developing a better future, then we'd better know what these models are doing, right? And that's basically the idea of interpretability. We have a paper in Nature Machine Intelligence that you can see here, where we also argue for more interpretability in the deep learning models, so that we can have a more comprehensive image of what is actually happening in these models. Focusing on the topic of today, of fluid mechanics, it turns out that there are also many success stories in this area. There is the seminal work of Milano and Koumoutsakos in 2002, who used neural networks to model the near world region of a turbulent channel. Some more recent work on LES modeling by Beck and others, development of turbulent inflow conditions, as Fukami and others have done also recently, or quite some potential in the context of RANS models, which are more oriented towards industrial simulations, as Duresami and others are pointing out. I also believe that it's quite promising, the whole area of flow control, as highlighted by Brantor and others, and a very interesting family of methods that I'm going to be discussing in this seminar today, and that's the idea of physics-informed neural networks, PINs, which allow us to exploit some of the characteristics of the neural network training in order to solve certain PDEs with some benefits. Okay. So what I'm going to start to discuss today is the possibility of doing non-intrusive sensing. Non-intrusive sensing implies that I can measure in one place. If we consider a channel flow, what you can see in this image is actually an open channel flow. So you have a wall at the bottom, you have the flow on top, and then you have an open surface over here, right? So non-intrusive sensing is interesting because you can use information measured at the wall to see what happens above the wall, right? So what happens over here. And that's important for many reasons, but one quite prominent one is the case of flow control. If you can know better what is happening on the flow, you can design a control more effectively to try to reduce the drag or to have better properties of the flow. And we are essentially, what we are doing is that we are taking information from this blue plane over here. We're using convolutional neural networks. I will tell you more about it in a second. And then we're predicting the flow quantities in this yellow plane over here, which is above, right? So we take information from the wall and we want to predict what happens above the wall. To do this, to train this model, we perform a direct numerical simulation using the Fourier-Chebyshev code Simpson. So we just consider a turbulent open channel. We start at a low Reynolds number, a friction Reynolds number of 180, and we produce on the order of 40,000 snapshots to be able to perform this training. All the details are found in this article by Guastoni and others, Journal of Physics Conference Series. And the whole point is that we want to use convolutional networks because they're very convenient for image processing. On the top, you can see a typical fully connected network, a multi-layer perceptron, an MLP. And the thing with these networks is that each neuron from one layer is connected to all the neurons of the next layer. What happens with this is that, first of all, you cannot exploit the spatial information in the data. And second, you have very, very large numbers of parameters. When you have a convolutional network, you have an input, you can see here, and then you have a kernel. This kernel is basically a window, a window that is sweeping through the image, and by applying convolution operations, we obtain what is called here the feature map. And as you can see in this example, I have a kernel of size 3 by 3, right? So 9 points, and each point of the feature map is receiving information from 9 points of the input. This these characteristics that these networks have are very beneficial for computer vision and image processing, as we will see in a moment. So essentially, to remind you what we are doing, we're using information at the wall to predict what happens above the wall, and we will use these convolutional networks to be able to exploit the spatial information in the data. So this is the architecture that we're using. We have a convolutional neural network with 3 input planes. The 3 input planes are the 2 components of the wall shear stress at the wall. So the stringwise and spanwise wall shear stress plus the wall pressure. So these are quantities that can be measured at the wall. And at the output layer, I also have 3 planes. I want to predict at a certain location the 3 velocity fluctuations of the flow. So the stringwise, wall normal, and spanwise fluctuations at a certain distance above the wall. What I'm also showing here is the number of hidden layers. So I have 6 hidden layers between input and output. And these numbers are what is called the feature maps. So the number of filters that I'm applying at each layer. So in the first layer, I have a filter which has a certain depth, and well, this is basically the size of the kernel. And what I'm doing is that I apply a total of 64 filters. So I stack this 64 times, which gives me a total of 64 feature maps that I can obtain from the input image. And each filter is identifying one or several features on the input data. Okay, and those features can be, remember that these are images, so those features can be lines or circles or regions of a strong fluctuation. So those are identified by the first layers. And each of the feature maps, each of these 64 planes is activated by one or several of these features of the input. Okay. Something quite interesting, actually, and here I'm showing you the full description of my setup. So I'm showing you the 3 inputs, the wall shear stresses and the pressure, and the 3 outputs, which are the 3 velocity fluctuations. What is quite interesting is that the first layers are identifying simpler features of the input, and because of the concatenated series of operations that I'm doing, the layers that are closer to the output are identifying more complex features, more complex things, right? So we are, in a way, building hierarchically more and more complicated things. So we are starting with lines and circles, and I end up looking at these streaky, complicated structures that the flow has, right? These are the structures that are present in the flow. And all this information, by the way, all the details of the setup can be found in this article by Guastoni and others in the Journal of Fluid Mechanics. And what we did is that we consider Reynolds numbers up to 550. So a friction Reynolds number of 550 is already quite turbulent, and it's already a Reynolds number that is quite convenient from the perspective of separation of scales. So I actually have a pretty good representation of the turbulence because I have enough separation of scales, and the flow is a bit more realistic, no, from a turbulence point of view. So this is actually quite convenient. And what I can do now is that I can define another method. So everything that I have told you so far is based on using all the information at the wall and predicting all the information at a plane above the wall. And this is what we call the fully convolutional network FCN approach, okay? Because my network only has convolutions. I don't have any connected layers. I only have convolutions, and my output is also an image, the same as the input. So it's an image-to-image prediction. However, there is another approach that we have also evaluated, and it's the so-called FCM POD. So POD, which stands for proper orthogonal decomposition, is the analogous in fluid mechanics to the PCA, the principal component analysis. They're basically the same algorithm. Essentially, what one does is that you have the spatiotemporal signal. So this is the velocity field as a function of space and time. You perform a POD, a proper orthogonal decomposition. So you separate your signal into spatial modes and temporal coefficients. And then in the FCM POD approach, we only predict the temporal coefficients. We don't care about the spatial modes. We only predict the temporal part because the spatial modes are known. Okay. So this is how the performance looks like for an instantaneous field. What I'm showing you is the stringwise velocity fluctuations. The third row, this one over here, this is the DNS. So this is the reference data. The first column is the result at y plus 15, which is a plane very close to the wall. That's the near wall region where you have the strongest fluctuations. And the second column is at y plus 100. So that's farther away from the wall. Okay, so first column is close to the wall, second column is far away from the wall. And remember that we are aiming at the third row. The first one is the result obtained with what is called the extended POD. The extended POD is formally equivalent to the linear stochastic estimation. It's basically a linear method that is connecting my input and my output. And what you can see is that the linear method is giving you something that is, on the one hand, quite attenuated, so the fluctuations are much weaker than in the reference, and second, is much smoother. So some of the details, nonlinear details of the data are not represented in the extended POD. And this makes sense, right? Because extended POD is a linear method, which means that the nonlinear interactions and turbulence is a highly nonlinear phenomenon. They're not captured by this prediction method. In the second row, what I'm showing you is the FCM POD, the one where I do the modal decomposition. And in the last row, I'm showing you the FCN, so just convolutional neural networks. What is interesting, if we compare these two, right, the third and the fourth, is that the prediction close to the wall using the FCN is almost perfect. I mean, it's almost identical. We get a very, very good prediction of the flow very close to the wall when I'm using the fully convolutional network. And when I go far away from the wall, the one that predicts better is the FCM POD, so the one with a proper orthogonal decomposition. And that's interesting. And it kind of makes sense because when you are doing POD, what you do is that you're separating the spatial and the temporal information. And when you are far away from the wall, you're encapsulating the spatial information of these very large structures into a few POD modes. So it's more efficient to just predict the temporal dynamics of those few modes when you are far away from the wall, because you're encapsulating the information more effectively. But when you are close to the wall, it's just too many scales and too many structures. So it's not so efficient to do POD, and you should just predict directly the whole signal. This is actually observed also when we look at the flow statistics. So I'm showing you as a function of the wall normal location, which is the horizontal axis, the stringwise, wall normal, and span-wise velocity fluctuations. The black line is the DNS, is the reference. The orange triangle is the FCM. The blue is the FCM POD. And the green is the linear method, the extended POD. And what you can see, if we look at the U prime, at the stringwise fluctuations, what you can see is that the near wall peak is on top. I mean, we get less than 1% error in that near wall peak. Of course, the predictions degrade as I move farther away from the wall. And that makes sense, right? Because when the input and the output are more separated, the signature of the input data, of the wall data, to make that prediction is much smaller. No, you have a structure here, and you want to predict it from this information. The signature on the wall is going to be much less pronounced. So the data is less correlated when I move farther away from the wall, and therefore the predictions cannot be as good. Regardless of that, you can see how farther away from the wall the blue dot is above the orange one, so the FCN POD works better, and the extended POD is always worse, right? So the linear method is not predicting so well because you don't capture the non-linearities present in the flow. Let me go to the next part, which is something that I believe is quite important in machine learning nowadays. And it's the concept of transfer learning. Transfer learning is basically the possibility of using what has been learned in one case for another one that is similar but different, right? So you don't have to relearn again that knowledge that has been embedded in the model. And if you look at the Arita 180 case, so that's the low Reynolds number. What we did was to have one model for predictions close to the wall, another one for predictions far away from the wall, okay? So the one, we train a model to make these predictions close to the wall, and the three first layers of the Y plus 15 model are frozen. So to make predictions far away from the wall, I only train the three last layers. And the rationale behind this is that the first layers are identifying simpler and smaller structures, and the last layers are identifying more complex things, no? More complicated features, larger scales, and more complicated ones. So the idea is that the small ones will probably be quite similar in the two locations, close and far away from the wall. And as you move farther away, then the larger scales emerge, and those are quite different. So what we did with this transfer learning was to just train the three last layers. And if we compare the performance and the cost, we see that the performance is very similar. So with the transfer learning, we can get the same level of errors, even if we are only training three layers instead of the six. And the training time was reduced by a factor of more than 4. Okay, so we can significantly reduce the cost of the training by exploiting what has been learned in another scenario. And this is actually very powerful. We did it also for another case, which I believe is quite important and quite interesting. And this is documented in our paper in the Journal of Fluid Mechanics, where we train a network to make predictions at Reynolds tau 180, so at low Reynolds number. And then what we did was to initialize the training at 550 with the weights that we have from the 180. So instead of starting the training from random values or from some initialized values, we just take the values that we have at low Reynolds number, essentially. And the point is that by comparing the losses and by comparing with the case where the initialization is random, what we realize is that we can reduce, again, the amount of training data necessary for the model at high Reynolds number. We can reduce it by a factor of 4 again. And what is the interesting thing of this? Well, a simulation at 550 is going to be several orders of magnitude more expensive than a simulation at 180. Keep in mind that to multiply by 2 in Reynolds number is approximately 10 times more expensive. No, so this is several orders of magnitude more expensive when it comes to computational cost. So if you can use a lot of cheap data to do an initial training and then reduce the need of expensive data, which is at high Reynolds number, by a factor of 4, then this transfer learning is something that we should be using, right? This is something that is quite convenient. In general, anything that you can do to make a more efficient training and to reduce the cost of your model development, or if you know something about the phenomenon that you're trying to model, then you should embed it in your model, right? You should not let a network learn something that you already know. As a general kind of practice, no, that we can have. So this is very promising, transfer learning, and I think that is really helping many areas within machine learning. And I think there are many topics that can benefit from more complicated architectures. What I have shown you so far has been only based on CNNs, on convolutional neural networks, which in the end, they are the most simplified architectures for computer vision, but there are more interesting models to analyze images, okay? So one of these models is what is called the GANs, no? The generative adversarial network. This network, you can see it here schematically. It works as follows. I'm going to consider this network is actually very widely used for super resolution tasks. So I'm going to consider that my input at the wall if you look at it here, instead of having all the information, as it has been the assumption so far, I only have few measurements, right? So I have a very, very coarse input at the wall. So what I need, first of all, is a very fine input at the wall in order to predict the flow above the wall with high resolution. And these GANs, what they do is that we have two different parts of this network. First, we get a generator, which takes a low resolution image and it produces a high resolution image based on targets. So this is a supervised learning approach. And these high resolution images reproduce the statistical properties of the reference data. Okay. And then the discriminator, its job is to identify if a certain image is from the reference database or if it has been produced by the generator, if it's a fake one. No? And these two networks, or these two parts of the same network, of the same architecture, they have antagonic roles, right? And they are trained together using game theory. So they progressively get better at their own tasks, so the generator can produce better and better images to fool the discriminator. And this works extremely well. It's a bit of an expensive architecture to train, but it gives you very, very good results. And what we can see in this example is that we create from low resolution images. In a first step, we create high resolution images at the wall. And using those high resolution images at the wall, we aim at predicting in high resolution the flow above the wall. Okay, so these are two steps. And we train those two steps together. So the goal is not to obtain perfect high resolution input images. This is just an intermediate step. So the goal is to obtain very good high resolution images above the wall. That's what we want to achieve. Okay. What I'm showing you at the bottom, and by the way, all these results can be found in the work by Güemes and others in physics and fluids. So you can see it here. What we can find this is the instantaneous wall shear stress, okay, in the streamwise direction. And I'm showing you on the first row different levels of downsampling. So I make it a factor of 4, 8, or 16 times coarser in its direction. And in the second row, I'm showing you the prediction. So I'm trying to obtain this field based on these input values that you have here. And what you see is that, I mean, for this input, which is extremely coarse, I mean, here you can barely see anything, but this is actually what you would get in an experiment, a few sensors here and there. You can actually get something that agrees quite well with the DNNs. I mean, of course, the fluctuations are attenuated, that's clear. And some of the nonlinearities are not so well reproduced, but you can see that the streaks are where they have to be. So they have the right spacing, they have the right size, and in the end, it looks very physical. That's the nice feature of GANs, that they look very physical, their predictions. So if you want to make flow control, well, perhaps this is good enough, right? Because you just need to know where the streaks are, and then knowing that information, you can define your control. So it's a very promising tool for non-intrusive sensing in experimental settings with very, very coarse data. So it's actually quite interesting. And these are the results above the wall. Okay, so what I'm showing you is the first row is the DNS. So this is the reference data. And then the columns are increasing distance from the wall. So this is y plus 15, 30, 50, and 100. So I go farther and farther away from the wall. And the rows after the first one denote the level of downsampling, so how coarse the input was, right? So clearly, this is the best prediction because this is the lowest downsampling and closest to the wall, and this is the worst prediction, no? Because I'm predicting very far away from the wall from a very, very coarse input. And even in this case, if you compare this panel over here with the one on the bottom, I mean, of course, I'm missing a lot of information, but still I'm identifying with the structures, right? I mean, I see where the streaks are, I see how long they are, I see their separation. So in the end, if I want to know where the structures are based on wall information, I am actually able to do it and obtain quite interesting and reasonable results. This parameter FD tilde is able to is used to compare results from different databases and different levels of downsampling. So because of course you cannot compare in the same way different resolutions, but using these parameters over here, we can actually do it quite effectively. Okay, so this is everything about non-intrusive sensing. And again, these GANs results can be found in the work by Güemes and others in physics and fluids. Okay. So the next problem that I'm going to look at is kind of like the opposite. I have been using the wall information to predict far away from the wall. What I'm going to use now is the information far away from the wall to predict close to the wall, not exactly at the wall, but close to the wall. And why is that interesting? This is interesting for what we call off-wall boundary conditions. So when you perform a DNS, a very result simulation, the resolution close to the wall is the finest. No? That's the most computationally expensive part of the simulation. So if you can replace that part of the simulation with just one boundary condition, then you can have a very, very significant saving, no, in computational time. So we use the information in the outer region to predict what happens close to the wall in that boundary condition. And to do that, we're going to use, again, convolutional neural networks. The work was presented in ETMM last year, and you can see the archive here. So you can see all the details in this archive publication. And what I'm showing you is the error in the predictions as a function of the delta y plus. So the delta y plus is the separation between input and output. So if my input is far from the wall and my output gets closer and closer to the wall, that means that delta y plus will increase, okay? And therefore, what will happen is that the predictions are going to get worse, no? The error is shown on the left, and the correlation between input and output is shown on the right. So the error clearly increases, no? As I increase delta y plus, because the input and the output are farther away. And what we also realize when doing this type of study is that there are two problems when doing the prediction from outside to inside compared to the prediction from the wall to outside. The first one is that the receptive field is small. If you're using as an input the outer region and the structures are very, very large, and your receptive field is very small, it's just a little tiny window, you're not really learning so much about the input data that you have there. Okay? And the second one is that at the wall, you have a very strong imprint of the large scales through superposition and some modulation, and it's present at the wall, it's present in your data. But if you do the opposite prediction, the input data doesn't have so much information about what you want to predict. You are going towards data that is richer than what you have in your input. And therefore, you have missing scales that complicate things a bit in this type of prediction. This was actually done, you know, if we want to rescale and to apply this as a boundary condition, this was actually done in a simple way by Mizuna and Jimenez some years ago, and by using a rescaling argument. And what we have here is so the first row is the input at y plus 100. The second row is the real data at y plus 50. And the third row is the prediction, the fully convolutional network prediction. This is, by the way, at 550, Reynolds 550, and the columns represent the string-wise, wall normal, and span-wise fluctuations. And what you can see is that the predictions are actually not that bad. I mean, if you compare this field with this one, I mean, the predictions are actually quite reasonable. We have, if I look at the errors, I have around 19% error in the string-wise velocity fluctuation. What is the problem? The problem is that you need much more accuracy than that, right? If you look at the spectrum, you see that we are missing a lot of the small scales. That's the information that we are missing in the instantaneous data. You can see it reflected in the spectrum. And we also see a little bit of a displacement in the high energy peak, right? So to solve this, some interesting directions could be, on the one hand, to solve the small receptive field would be to do some max pooling at the beginning, or some treatment of the data, so we can get much more information encapsulated in an input that we can then process through my convolution. And the second one, to address the lack of scales that I'm actually missing, could be to do GANs, for example, to look at some GANs-based reconstruction in order to reproduce some of those missing scales. In any case, the problem of world boundary conditions is very complex, and just doing the prediction, a supervised learning to predict the correct data at that instant might not be even enough. It might be necessary to do other approaches that are a bit more complex and that take into account some statistical features of the flow. Okay, but still, this is a promising direction that I believe is important to explore. So, some other things that we're working on is what we call a nonlinear modal decomposition. Okay, so the POD that I showed you before, this is a linear modal decomposition where you are just having a bunch of modes, and then you linearly superimpose them to reproduce the original signal. However, it's possible to use autoencoders, which is a type of deep learning architecture, to have a much more efficient way of encapsulating, of compressing the input data. Autoencoders are very good at, you have an input, you compress it in the latent space, and then that's the encoder part. The decoder is reconstructing the original signal, and in that latent space, you can have a compressed version of your data. And there are different ways of defining these autoencoders for modal decomposition. You can see our work by Vinuesa and others. It's in archive and it's now accepted for publication as well, so you can check it out there. The trick is that we can use what is called hierarchical autoencoders. So if you do it in a hierarchical way, this modal decomposition, you can actually get a set of modes that are sorted in descending energy content. So the most important modes towards the reconstruction are first, and then the energy content goes down. That's hierarchical. Another property that is very important in these modal decompositions is the sparsity of the model, is that you get modes that are orthogonal. Basically, that a certain physical phenomenon is not mapped into more than one mode, no? So there is not any overlap between those modes. And that can be obtained by using beta variational autoencoders. These beta variational autoencoders allow us to impose a penalty in the latent space in order to enforce that orthogonality of modes. And as you can see in this figure over here, that represents the orthogonality of the 5 first modes, they are essentially orthogonal. So we are able to, with autoencoders, obtain a modal decomposition framework, which on the one hand is hierarchical, which means that I have the first modes first, right? The modes of more energy are first, and then I can truncate, then I can take the ones with most energy and truncate. And second, they are orthogonal, which is very good for interpretability of those modes. And this is tested with a DNS of the flow between 2 obstacles. This is a little urban environment. This is the reference instantaneous data, and these are the various predictions with different autoencoder-based decompositions. The POD, if you reconstruct the flow with POD and you take the 5 first modes, what you get is this. Only 32% of the energy is reconstructed, so you get something that is very far away from the original. If you use autoencoders, you can get up to 95% reconstruction, but our autoencoder that is orthogonal, the one that we believe has better properties from a physical point of view, is this one, and we get almost 90% reconstruction of the whole signal. So this is very important. This is very helpful for ROMs, for reduced order models. If you need hundreds of modes with a POD to reconstruct a signal, your ROM is going to be very complex. It's not going to be so practical. If you can do it with 5 modes, that's actually pretty cool. You can actually predict pretty well 5-time series, which are the temporal coefficients of those modes, and effectively build a very good reduced order model like that. So I think that nonlinear modal decomposition with deep learning is a very, very promising area of research to analyze and simplify turbulent flows, which are very high-dimensional systems. So they are quite complex to understand and detangle, and these approaches are quite promising in that sense. Now, another approach that I think is quite interesting, and you can find the article here in archive, also by Vinuesa and others, is to use physics-informed neural networks, PINs, and this is one of the areas which I believe is interesting, is RANs, for Reynolds average and Stokes equations. So what are the RANs equations? The RANs equations, which you can see here in 2D, they are basically obtained after applying Reynolds averaging, the Reynolds decomposition and averaging to the Navier-Stokes. So what you have is the governing equations of the mean flow. So the capital letters are the mean quantities, but you still have the Reynolds stresses. No? Even if you have the equations for the mean flow, you still have the Reynolds stresses. The idea is that traditional RANS models, they have some assumptions about the behavior of these Reynolds stresses, and they model them, assuming something. They have a certain empirical model for Reynolds stresses, and industrial simulations work better in some cases, depending on your calibration data, but not so well in other cases, and that's a challenge, essentially. What we want to do is to use pins to solve the RANS equations without assuming any model for the Reynolds stresses. So we can actually just solve the RANS equations with the Reynolds stresses being part of it, okay? And what we do for this is the following. We have the computational domain. We need to provide boundary data. These are the red dots here. And then we solve the equations in these collocation points. Of course, our learning, our loss function has two parts. One is the residual of the RANS equations, because we are solving the RANS equations. Another one is to match the boundary conditions. So the network, or the algorithm that we are designing, what it's doing is that it's a way to solve PDEs, partial differential equations, by exploiting the automatic differentiation of training. When you're doing a training of a neural network, you use automatic differentiation to calculate the variation of the loss with respect to the weights in the different layers. No? So you need to differentiate in an efficient way. And that automatic differentiation gives you exact values of the derivatives in those points, essentially. Now, the key is the following. When you have a finite volume or finite element, some discretization of the PDEs, right? You need to solve the gradients. In this case, close to the walls, you will have gradients, and you will need very fine resolutions there to be able to resolve those properly. And that requires a certain measure solution. In pins, you don't need in principle to resolve the gradients because the derivatives are already exact, they're already very accurately calculated. So you can solve the governing equations in a coarser mesh than you would have in a discretized form of the domain, because of the possibility of evaluating those derivatives accurately. And that's beneficial in certain cases. We are actually comparing the computational cost of our pins simulation with a regular run simulation. The cost is very similar, but with the advantage that we don't need to invent a model for the Reynolds stresses, because the Reynolds stresses are solved together with the equations. Okay, so that's one area of quite some potential that comes from the pins framework, that you can see here. So actually, something that is quite interesting is that we can look at different cases. No, we start with Fallner scan boundary layer, which is a laminar boundary layer with a pressure gradient. And what we can see, we can predict the mean velocities, the U and V, and the pressure. We can, I mean, of course, this is not a very interesting case, right? Because this you can solve, analytically very, very easily. No, this is not, but this is a first test, to see how this will perform. And actually, you get less than 0.1% error in these quantities, which is quite promising. So I am able to solve this case that is laminar. But when we go into turbulent cases, then some more interesting things happen, right? We look at the zero pressure gradient turbulent boundary layer, which you can see here. This is DNNs data, and at a Reynolds number based on momentum thickness of 7,000. And what we're going to do is, remember, with RANS, we're going to look at turbulence statistics. So given the boundary conditions, I'm going to calculate the turbulence statistics using pins, and I'm going to compare those with the turbulence statistics obtained from the DNS. And that's the comparison that I want to make. And remember that my performance, well, my cost is similar to that of a similar RANS, but my performance is actually quite surprisingly good. No? If you compare the mean flow, and even the Reynolds shear stress, I mean, I get 1% error in the mean flow and 6% error in the Reynolds shear stress, which is much better than you would get with a traditional RANS model. I mean, the Reynolds stresses are very challenging for Rans models, and the mean, we have a very, very good accuracy. You can see here that the boundary layer development is actually very well predicted when using physics in for neural networks. If we go to more complicated cases, this is an average pressure boundary layer. So this is a boundary layer that is decelerated, and the data is actually found in this work by Bobke and others in the Journal of Fluid Mechanics. This has a constant pressure gradient of around 1, and so it's a moderate pressure gradient, but constant, so the boundary layer is in near equilibrium. And what you can see is that now we get less than 0.5% error in the mean, and very good predictions again of the Reynolds shear stresses. So you can compare the mean flow, the fluctuations, the boundary layer development. So even in this case, that is quite challenging. Looking at a pressure and boundary layer, we can actually get quite good results. A much more challenging case is a wing, right? Because then you have a turbulent boundary layer where the pressure gradient is in non-equilibrium, right? So you have a very quickly growing pressure gradient, and we're going to look at a well-resolved LES database by Vinuesa and others. This data, you can find it in the Journal of Heat and Fluid Flow. So this is well-resolved LES data, almost DNS resolution, up to Reynolds number of 1 million. So you actually have many different cases here, and you can see the flow quality. So this is DNS data of wings, and we're going to pick the case at a Reynolds number of 200,000. So a moderate Reynolds number, but turbulent, completely turbulent, as you can see in this visualization. And what we see is that even in this case, which is very challenging, we get 1.5% error in the mean, and even the fluctuations we get well up to 10% error. But this is something that it's much more accurate than what you would get in the context of a run simulation. So we can predict very well the flow in terms of its statistics, no? So the mean and the fluctuations, given the proper boundary conditions. Even flows like the periodic hill. The periodic hill, which you can see here, is a very common case for testing runs models because it has separation and reattachment. So to be able to predict with runs the reattachment location is actually quite promising. No? It's actually quite interesting. And you can see that the recirculation bubble in the prediction and the reference, they are in very good agreement. So even in this complex case, remember that runs models typically have a lot of challenges predicting the separation and reattachment, but even in this complex case, with pins, we can get less than 3% error in the mean and very good predictions also of the fluctuations. So we get a very good representation of the flow, even in these complex situations, which have quite some separation. Yeah. So pins is very promising. Of course, we are working on improving some of its properties for unsteady flows and for more complicated situations. But from a statistical point of view, the results seem to be quite interesting and quite promising. And one of the last sections that we have is basically the use of flow control. No? So deep reinforcement learning to apply flow control, to be able to, so that the algorithm tells me how to control the flow instead of me imposing a certain law on that control. And reinforcement learning works as follows. No? This is another machine learning algorithm. It's called deep reinforcement learning when we do the learning with a neural network. So that's a deep neural network. So that's kind of a very promising direction. So essentially, we start with an agent, and that agent is interacting with an environment. The environment is basically the flow simulation that we have. So the agent interacts with the environment through some actions at instant t, so AT, and the environment returns to the agent with an update on its state, so the state at t+1. Yeah? And we also have a reward from the environment. Yeah? So at instant t, we get a reward, which has also, it produces a certain action, and it moves the state to the next step. And that's what triggers then the next action that is going to be carried out in the environment. The key is that the reward is a measure of the quality of those actions under a certain norm, some norm. It's not clear, depends on what you're looking for. No? But that's the idea is that you want to maximize the reward through the actions of the environment. And this is something, something that I mentioned at the beginning, no, when I talked about the Alphago 0, no, that was playing against itself, trying things. This is the idea, the reinforcement learning, that the agent is trying different combinations, different actions, and progressively learning the ones that maximize the reward, which that's basically the goal of the DRL. We want to define a policy pi such that we obtain the actions at instant t, given the state of the system at instant t. So given the state, I can choose the actions so that I can maximize the reward. Okay. And these are some initial results that we presented last year in the APS. We consider a 2D flow, a 2D channel, where we impose suction and blowing on the top wall in such a way that we produce a separation bubble on the lower wall. So we have this bubble, and we have a control region upstream of that bubble, which is aimed at minimizing the bubble length. So we want to be able to minimize the bubble length. This is a simple case where we know that periodic forcing is the classical approach to minimize the bubble length, and we want to see if the reinforcement learning can perform better, essentially. And this is the setup. So what we have is that we obtain the state of the flow through these 24 probes that you can see here. The control is by means of forcing, so it's this green square, and the reward is the bubble length. So this length over here, we want to minimize it, and that's basically the idea. And in this visualization, these color contours are the ones of the bubble, so the ones with negative velocity. We just want to shrink that negative region as much as possible. So this is what the DRL does. This is a video that is running now. So what you can see is that the reinforcement learning is sending, in a way, waves with two frequencies. There is one frequency that is clearly identified, is this wave packets that you can see here. And there is another frequency that is associated with the characteristic length of the bubble. So interpreting the output of the DRL is a bit complicated, and that's something to look at, to understand a bit more what it's doing. But if we compare the bubble reduction with the periodic forcing, which is the classical solution, we obtain a bubble reduction of around 30% with the DRL, compared with a reduction of around 20% from the periodic forcing, approximately. So it seems that for this simple flow case, we can actually outperform classical solutions. And we're currently expanding to do this type of control in channel flows, so in a more complicated 3D environment with turbulence, but that's of course ongoing work. But it seems that there is quite some potential in the context of these simplified flow configurations. Okay, and this is a summary of my talk and my conclusions. We have done non-intrusive sensing with DNNs and GANs. We have been able to obtain nonlinear model decompositions with autoencoders. We have applied pins for runs, not really modeling, but for run simulations in the context of complicated geometries. And we have also presented deep reinforcement learning control for simple flows. I would like to thank you very much for your attention. You have my information here for my email and my web and my social media. So if you want to contact me to ask me anything afterwards, feel free to contact me. I'm always happy to discuss and collaborate. And yeah, thanks very much. And I will now take the questions of the audience.
Thank you so much, Ricardo. It's been really impressive to see all the evolution in your work regarding the application of neural networks, in this case to turbulence modeling. Well, just before translating you questions in the audience, may I begin by asking you some questions, because at the beginning of your talk, I was a little bit surprised in your interest in applying neural networks to compute a POD projection, which is actually linear. But finally, you solved my doubts, because you then switched to autoencoders to actually obtain a non-linear projection. So my question was about the interest of having actually a linear projection, like in this case, for such a complex problems, which is turbulence. Is it interesting, or after the employ of autoencoders, this loses the interest?
So that's a very good question. So at this stage, the interest of doing the decomposition is not to obtain a reduced order model. When I do the autoencoders, I want a reduced order model, but here that's not the interest. The interest is to get better predictions, to be able to encapsulate the information in some way that I get better predictions. So when I do the FCN, I am just predicting the whole signal, the whole plane. When I do the POD, I only predicting the temporal part of the signal. Now, why does the linear decomposition work okay for this type of prediction? This is something that I didn't explain in the talk so much because it's a detail, but I think it's a good moment to explain it. We have these little cells that you can see here, right? So we do, and we choose POD because it's very easy. It's very easy and straightforward, and it's not time consuming to do the autoencoder and so on. It would take more time, no? So in each of these cells, we do a POD. And then these cells have a certain size, which is not so large. But for the POD, any scale larger than the size of this cell is lumped into the first mode. So a lot of the larger scales are lumped into the first mode. So what happens is that without too many modes, if I remember correctly, it's on the order of 40 or 50, I can actually reproduce most of the original signal. So for each of these squares, I need to predict 40, 50 coefficients to get a very good representation of the signal and get a good prediction of the overall flow. And actually, depending on the size of this grid, you may have discontinuities between the different cells. But if you have, with a little bit of a study on that, at some point you get very smooth signals, which are actually smooth for the spectra as well. So this is not really problematic if you have enough of these little cells. So yeah, to kind of answer your question, we did a POD here because it's fast and it fulfills the role, which is to some of the information of the signal encapsulated in the spatial modes and only predict the temporal side. This could be done with autoencoders, yes, but of course one needs to see also the speed of developing that decomposition compared to POD, but that's certainly one area that could be interesting. But this is not to do a ROM. This is just for prediction purposes only.
Okay, it's clear. Thank you. Well, we have some activity in the chat. First of all, gave Weymouth sent you a message. Interesting stuff, Ricardo. I need to head off. I'm sorry because I assume that this is due to the delay in the beginning of this talk today. But he says I enjoyed the tour through your recent work. Well, this is more a comment than a question. In any case, Sulkifal Dar is making a question. Regarding the pins case, does the training set include the Reynolds for which it was later used to predict results? If not, approximately how many different Reynolds and with what range were used for training?
Yeah, so that's a good question. One clarification, in pins, you don't have a supervised you only have part of a supervised approach, but you are not really matching a certain data at a certain Reynolds. You're just solving the equations. You have the Reynolds equations, and you're solving the equations. You're, in a way, using the tools from neural networks to solve a PDE. So in that sense, it's a bit of a peculiar approach, pins. The Reynolds number would come in the boundary conditions. So whatever boundary conditions you're setting, that's telling you what the Reynolds number is. And you need boundary conditions for your case that you want to solve. So it's implicitly embedded in the boundary conditions that you're using. But you don't train for a particular Reynolds number. That's not a parameter. The only thing that you need to do is to solve the governing equations for that set of boundary conditions that you are providing.
In particular, I have appreciated the fact that you call collocation points, the points in which you evaluate the PDE within the framework of pins. I think this is not the standard, but it's like like a collocation method, actually.
To some extent, yes, exactly. And of course, this is a good discussion, no? Because if you have a PDE, I mean, the best way to solve it generally is to discretize it with a proper numerical scheme, depending on the accuracy and the stencil that you want to use, and that's typically the best way to solve it. But the advantage, so if we had the instantaneous runs, the instantaneous Navier-Stokes, probably a finite volume approach is going to be more effective than pins. The reason why pins is more effective here is that it allows us to solve the Reynolds stresses. But in general, for the general case, a numerical method will be more effective than pins for the general case. But in some particular cases like this one, pins is actually more effective. So it's a bit of an interesting assessment, no, case by case, for which is the approach that could be more interesting.
Mm-hmm. Another question in the chat. In this time, Carlos Hernandez says, "Great talk, Ricardo, regarding the oversmoothing in CNNs. Have you tried some kind of frequency encoding to better learn the higher frequency, the details of the flow images?"
Yeah, and that's another very good question. I mean, there are different approaches that we are considering there. The biggest problem is that the data, the input and the output data stop being correlated, you know, when the target is very far away. So it is difficult to really do that, to really get more insight from the input to make a good prediction of the output. That's why you are smoothing it. But I mean, the approach that you propose could be something interesting. Something that we are looking at, that I think could also be quite promising, is to have a network that is making predictions in intermediate planes. So you are having a network that is not predicting directly at 100, but you predict maybe at 50, and then at 30, and then at 100. So progressively and recursively doing those predictions by getting data that is more highly correlated in between, which in a way is a bit in the direction of what you're saying, of encoding some of those frequencies. You're just predicting planes that are more highly correlated to get an overall better prediction in the end. So it goes a bit in that direction. We are trying that, and it seems that it's promising. So maybe in the next talk, I will tell you if it works or not.
Talking about the future, Ricardo, I don't know if you have any experience regarding the employ of neural networks to learn closure models for turbulence.
Yeah, that's we have one paper on that, and I know several people looking at it, and I think there is promise, and it's an interesting direction. But one should be a bit careful, no? Because I mean, someone should be careful with the data that you use to train the model, right? Because if you use DNS data, just DNS data for certain terms, those terms statistically may make sense, but might not be fully consistent with the RANS formulation, no? So sometimes this happens a lot with LES modeling as well, right? It's not just about taking the DNS and filtering and then training a network to help you for what you have filtered. It's not really like that, because when you start to have coarser resolutions, then the physics starts to be distorted. And then it's not about using perfect data to compensate what you don't have in your model. It's more about finding a method that gives you what you don't have in your resolution consistently with what you have. I don't know if I explain myself. It's not just about filtering data and compensating. It's more about having a consistent simulation on its own. And it's not so straightforward, but it's one of the directions to go. I mean, RANS modeling, LES modeling, the boundary conditions that I mentioned, things like that machine learning can actually help.
Mm-hmm. Great. I don't know if there is any more question in the chat. Apparently, no. Carlos Hernandez thanks you. But
thanks.
well, if it is not the case, if there is no more questions, I think it's time to thank you, Ricardo, for this wonderful lecture, to agree to this invitation made by our society, and to make your presentation available in our YouTube channel. So just an announcement that it's in any case well known that you will be present in our conference in September in Las Palmas. Yeah. So we will be happy to meet in person. So, well, Ricardo, again, thank you so much for being with us today. And, well, see you in September, if not before.
Thank you very much for your kind invitation. It was a real pleasure to be here. And yeah, see you in September, if not before. And thank you very much. Bye-bye.
Thank you.
Thank you, Ricardo.
Thank you, Irene. Thank you very much.
Bueno.